Okay, time to talk about friction. This video will just be the intro to get you up to where the other class was yesterday. We didn't quite get as far because of the shorter class today, okay? So, what do you know about friction? Well, hopefully you know that every surface has some. Every surface has some friction. Okay, how much each surface has depends upon the texture of the surface. Rougher surfaces are going to have more friction. Smoother surfaces are going to have less. So, how much friction a surface has depends on, we could call it texture or roughness of the surface. Okay, friction, now what I mean by that is, like, if you think about your table or lab bench in the classroom, like, it might look smooth, but if we were to magnify it, you would actually see that it has a lot of little bumps. And so then friction is about these little bumps slowing down an object that's trying to move across it, perhaps. Obviously, rougher surfaces, the bumps would look more like sharp points. So obviously, a box on this surface and a box on this surface would experience different amounts of friction. So roughness or texture of the surface plays a big role. But what is it really? It is a force that always opposes motion or the desired direction of motion. So it always opposes motion or the desired direction of motion. Opposes means it always goes against motion or the desired direction of motion. So, and like obviously opposes motion. If I'm pushing a box this way, then like pushing with a force like this, then friction's going to act backward on it. It's going to oppose motion. But what do I mean by the desired direction of motion? Well, it might be that I have this box here and that I'm putting a force forward on it, and yet I'm not able to make it move. Maybe it's on gravel or something, so the surface is quite rough. And you're all, of course, watching me, and it's like, I just don't understand why I can't make the box move. So I'm standing, of course, on this side, pushing that way. And you would all say, well, it's probably because of friction, because friction is acting opposite you, opposing the direction of the motion that I want to make happen. So it always opposes the motion, if it's actually moving, or the direction of the desired motion. There's actually different types of friction, and one type is called static, and we'll get back to this in the next video. Static friction is the friction acting when objects are at rest. And the other type, when the objects are moving, is called kinetic friction. So we'll come back to these, so you don't have to worry about me not giving you good definitions here. I will in the next video. But just so that you know that friction isn't just always acting on objects that are moving, also acting on objects that are at rest, right? And so I might say, oh, if friction's acting back that way and I'm trying to move this object to the right, then I don't care. I just needed to get it out of this way, so I'll just walk around and I'll push from this side. But if I walk around and push from this side, friction is going to flip too. So friction will always oppose the desired direction of motion, okay, or the motion itself. So what else is friction dependent on? So it's dependent upon the roughness and the smoothness of the surface, like we said up here. How much friction a surface has depends on the texture. The other thing it depends upon is how closely these surfaces are pushed together, right? So if I draw my surface down here again, and I put my box on it, like how much this box experiences these bumps as it's moving along is dependent on how closely these two surfaces are pushed together. For example, think about when you were a little kid in a toboggan and you could like fly down the hill so fast in the toboggan, right? And then as someone, an adult, as someone larger comes along and says, "Oh, can I get in on the toboggan with you too?" And when they get in, then you sink more into the ground and into the snow. And as a result of that, you don't fly down the hill as well. Okay? So the two things that friction are dependent on, one is how rough or how smooth the surface is, and the other is how closely these two surfaces that are in contact are pushed together. So we know that the force pulling this top object down into the surface is Fg, but it's the normal force pushing back up that's going to seal them together. So the second thing that friction is dependent on is the normal force. So it depends on how should we say it? How closely the two surfaces are pushed together. How closely the two surfaces are pushed together. And this is determined by the normal force. Okay? In actual fact, the force of friction is directly proportional to the normal force. So friction is, remember in high school science, high school physics, all forces are capital F's with a subscript to tell us what's causing it. So friction is F with a subscript F. So friction and the normal force are directly proportional to each other. In other words, if the normal force doubles, friction will double. If the normal force triples, friction will triple. Okay, so we say they're proportional to each other, or we say that their ratio is a constant. So friction divided by the normal force is equal to a constant. And this constant is called the coefficient of friction. Coefficient of friction. And it's a constant for a given surface, but changes from one surface to another. And the letter for the constant is, we use the Greek letter mu. It's the same symbol that we use for micro in units for the metric system. And so our equation, we don't usually write it like this. We usually write it as friction is equal to mu Fn, where mu is the coefficient of friction. Okay, Fn is the normal force, and friction is Ff. So if you look at the fact that the coefficient of friction is equal to the force of friction divided by the normal force, you should be able to see that mu is not actually going to have any units, because it'll be newtons over newtons. So mu doesn't have any units. And you should be able to see too that the bigger mu is for a given surface, the bigger friction is going to be. So the bigger mu, the rougher the surface. And mu usually has a range of values between 0 and 1. So ice at Willie O'Reed might be something very close to 0. Gravel outside might be something close to 1. Okay, so this is the equation, and it's known as the fun equation because in university, friction is usually written with the script F, mu is mu, and the normal force is usually written as a capital N. And so the equation tells us what we already know about physics. It's fun. Okay, so the next video we'll talk more about friction in the